We are recording. Okay, I'll look at the people, not at the monitor there. Okay, so field of view. So that's for today. So it's not just field of view. It's field of view and voxel size and the matrix size. All those things are interrelated, and so we'll hopefully try to get some intuitive feel for it with a bunch of examples. But before I do that, I wanted to, so last time I mentioned that there were a couple of things going on. There was the fact that in our original equations we infinitely finely sampled out to infinite spatial frequencies. And so there were two things going on when we actually collect real data. So two conceptually different things. So one of them is we just discretely sample the frequencies. There's a space between each spatial frequency, delta k, so that's the step in spatial frequency. And then the second thing was that we weren't going out to infinitely high spatial frequencies. So, and those have two different effects. And so I thought I would just go over the basic argument for why you get something called ringing, the thing I described as ringing. So just to quickly reiterate about the generation of replicas, which comes from the fact that you're discretely sampling with the delta k. Just quickly go over that one again. So assume that you've got, a brain with space around it. If you Fourier transform that, then what you get is, and you get into spatial frequency. And so what we're doing here is an example of the convolution theorem, which says that if you multiply in one domain, if you Fourier transform the stuff in that domain and go to the other domain, you have to convolve, or vice versa. So if we look at this Fourier transform here, what we get, it's something like a sink. So here's a sink. And that's kind of what the brain, if you look at a Fourier transform of a brain, it will look more or less like a sink. It's got a big bright spot in the center and then little ripples going out. And then the problem was we sample that, and so this is the multiply side. So if we sample on the spatial frequency side, that's the data that comes off the scanner, then we have, here's our little sampling bed of nails sampling function. So it's just it's an infinitely thin spike at each spot, and we just go up and get one sample out of that sinc function, which is what the spatial frequency data looks like. Then that equals just something that's you just got 1 point here, and 1 point here, and 1 point there, 1 point there, etc. So etc. So what does that do? So what that does is it makes the replicas. So we start off without any replicas. You just have one brain and there's an infinite amount of space. So how do we figure that out? Well, if we take the Fourier transform of this thing, you can actually Fourier transform it. If you look in the notes, there's the equation for the Fourier transform, but it works like other Fourier transforms. It makes this setup where as you make these guys closer together, these guys get further apart. So then how do we figure out what our result in space is we have to convolve on this side. So this is convolution. And in the special case, when we've got just a spike, what it does is it just makes a copy. You can think of it as sort of blurring the spike by this function. This is like your filter in Photoshop. And so it blurs the spike into a brain. And so what you end up with is, brains going on forever. And so they're supposed to be the same height. So that's the replicas. And so how do you change the replicas? Well, if you sample denser here, that's going to make these guys get further apart. So that's how you push out the replicas, denser sampling. So that was the first effect, which was that we're not sampling infinitely fine steps in spatial frequency, just discrete steps. But the second one was the blurring, and we can do the same sort of operation to sort of figure out the blurring. So if we start again, so here's the space side and the spatial frequency. So we can use that same argument for when we cut off spatial frequencies. So the way this works now is we got the image again. So here's a brain image, brain air on either side, it's dark. So when you Fourier transform that, what do we get? Well, we get a sink. Like when you start doing the Fourier transform homeworks, you'll see, when you do the Fourier transform, you get a really bright spike in the middle, and then it tends to ripple. It sort of gets dark light, as you move away from the center of K-space. And that's it's roughly what you would expect from something that kind of looks like a boxcar. It's bright in the middle, and it's dark on either side. So now what we want to do is, instead of sampling it, what we want to do is just cut it off. So say here's the maximum part of K-space, so then we'll make a bigger boxcar. And so on this side, now we're multiplying on this side again. So if we multiply by, so this is cut off, high spatial frequencies. So what does that Fourier transform into? What that will end up. So this initially went on forever, but now it gets cut off. And so we want to see what the effect of that is, where it just gets cut off right here by this other rectangle function. So it just stops. So what does that equal? Well, if we Fourier transform this guy, what do we get? We get an even smaller sink. So we get like a really sharp, spiky sink. So here's a little spiky sink like this. In fact, it's only 1 voxel wide. This sink, if you do the calculations, you'll see that this sink is exactly 1 voxel wide, and then this point here is the 0 point is the next voxel, and then the next 0 is the next voxel, and the next 0 is the next voxel. So you get a tiny little thin sink, and then if we convolve that with this function, then it's like a Photoshop. This is our Photoshop filter on this function, and so what will it do? It will sort of blur it with this little rippley thing. And so what will it make? If I what it will make is here's where it would have been, but instead what will happen if you convolve this with 0? So what is a convolution again? A convolution is basically a correlation. It's just like a cross correlation with a sign change, but it's basically the same as it has this. The amplitude of it is the same as a correlation. It's just that you have to sort of flip it around for the convolution versus cross correlation. You just paste the function over a particular part of the thing you're convolving with, and then do all the correlations. So if you take this thing and multiply it by 0, you get 0. If you take this thing and multiply it by a flat number, you get the same flat number, except when you get to the edge. So when you get to the edge, what's going to happen? Well, this thing looks like a rising edge, and so that kind of looks like this. And so it's going to correlate with it. And so what will happen is, of course, this thing doesn't look like a rising edge, and it won't correlate with it. But what will happen if you actually just work through the math, you'll see that what happens is, as you get close, you start to get little ripples like this. And then when you get up to the edge, you get a ripple up there, and then it goes down and then back. I've exaggerated how big it is, but that's what you get. So that's the ringing. That's what we call the ringing. The unfortunate aspect of this is called Gibbs ringing. But the unfortunate aspect of this is that if you can't make it go away. So if I blow it up a little bit, so here's that edge. So okay, so this is blown up. Magnify. So it turns out if you sample more densely, so if you do this thing, if you shrink it in, sample more densely, you would think maybe that would help the problem. But in fact, all it does, it doesn't change the height. So it unfortunately doesn't change the height. And so what happens is it will make the ripples finer, like this. But sadly, the height of the ripples does not change. So it's supposed to be here. So you'll get a fixed height of the little ripples at an edge. That's called Gibbs ringing. And the argument is here. If you sample more finely, you can sort of make the voxels smaller. So not sample more finely. What I meant was, if you sample out to higher spatial frequencies, not sample more finely. So if you sample out to higher spatial frequencies, you figure maybe that would sort of get rid of this thing, but instead what happens is it keeps the spike height the same, the little ripple height the same, but it just makes the voxels smaller. So you can fix that. That's always there. You can fix that by just smoothing a little bit, because this is a huge sharp edge, and if you smooth that a little bit, you'll just end up with something that has none of it left, like that. So this guy is, very light smooth. But that's just kind of a side effect. So this, let's annotate this side at the end. So this one was, finite sample interval. Infinite freaks. So you go out to infinitely high freaks. This one was finite sampling range. So that was finite sampling range. This was, finite sampling interval. So those have two different effects. So now, that's hopefully somewhat intuitive. Now you can write all these things out with equations. I find sort of the graphical approach kind of more pleasant to think about, because it's you just always have sinks, and you've got boxcars, and but you can write all these things out with equations. It's a little more wordy with an equation, but it's kind of convenient to just reason about things this way. Okay, so what we're going to do now is talk about field of view and give some examples. So I already gave one example. So one example I gave, I'll do 4 more examples of field of view. So I already gave one example when we talked about what happens if you sample out to the same spatial frequency. It was the bottom row in the last lecture. So what happens if we sample out to the same spatial frequency but increase the sampling interval? And so we said what that does is that causes the replicas to move in. So let's just give some more examples that are slightly more relevant to what you might run into on the scanner. And because the field of view is so counterintuitive, it's got an intuitive name, but normally you're not thinking of replicas when you think of field of view. You just think of like I've got some concrete space inside the head coil. That's typically the way you think of the field of view, but it's actually related to the replicas. So what is the field of view? So the field of view. So that's a nice, crisp, bright one. So the field of view in the x direction is unbelievably simple. So it's just equal to 1 over the sampling interval. That's kind of like, it's just not that's such an easy equation. So whatever the sampling interval is, however many cycles per image, one of the units would be like 128 cycles per image. That would be a high spatial frequency. You basically just take the reciprocal of that, and that's the field of view, amazingly. So we'll just write that out. So FOV, what it really means is distance to repeat. Is reciprocal of sampling interval. That's it. And somehow that's very unsatisfying. Like when I look at that, it just doesn't do anything for me. It's just somehow it just doesn't seem right. But that's what it is. Now, what about the voxel size? So the voxel size, we'll call that guy delta for sort of the voxel size. So the voxel size is basically just the field of view in the x direction divided by the number of voxels. So you could rewrite that as 1 over the number of voxels times the sampling interval. So basically just this pixel size, voxel, pixel, volume or 2D element, just is field of view divided by number of voxels. So that's not surprising. So let's just use these calculations just to sort of see what happens when you vary things in k-space. And so we'll start off, I'll do 4 of these across the board. So we'll start off over here just with a basic image. So here's a basic image where things are kind of more or less set up correctly. So for our basic image, we'll have spatial frequency data we collected, and then our reconstruction down here, image down here. So let's start off with sort of a nice square like this. of K space. So that's spatial frequency space. So spatial frequency over here. And say our sampling, so there's the center of K space, and so say we do 1, 2, 3, 4, 5 samples, and I'll have two-dimensional K space, so that's our sampling rate. And so if we kind of summarize that, using these equations, so we've got, so we have the number of voxels equals 10. You have to sort of deal with the fact there's a center of K space and then 5 on either side. That's 11, but one of the edges belongs to the next replica. So the number of voxels is 10, and the highest spatial frequency is 5 cycles per image. And the sampling interval, so the delta kx is 1, because we're just doing, this is 5 cycles per image, 4, 3, 2, 1. And then, so what is the field of view? So the field of view equals 1, because the field of view is just 1 divided by 1. And what is the voxel size? So the voxel size equals 0.1. Because we've got 10 samples divided, 1 divided by 10 is 0.1. So that's our starting position. And if we reconstruct that, so this is space down here. So if we reconstruct that, then we will get a basic image. So here's our image. So there's a brain there. Oh, why did I suddenly draw the other hemisphere? Okay, so let's draw so here's the brain. And there'll be, a replica over here, but it'll be off the edge. So there's a replica over there, and there's the replica up here, down here, over here. And if we look at the voxel size, since we're sampling the same in the x and y direction, let's just say the voxels are this big. Okay, so those are our voxels. They're uniformly, so this is, K, Y, and KX. KY. Okay, so that's our basic image, and it's just the for ft minus 1, the inverse Fourier transform, which just has a plus, and so that gives us our image. So now let's start messing around with it. So the first thing we might do, there's a lot of variables here, so let's, so the first thing is try same number of samples. So same number sample to higher spatial frequency. So same number of samples to higher spatial frequency. So in this case, so here's our original K space, and we'll just do it in the x direction. So if we go out to here, we're doubling our spatial frequency coverage. So we have a rectangular K space, but we're not changing. So we took out 1, 2, 3, 4, 5 over here, but now we've just got like 1, 2, 3, 4, 5 over here also. So you keep the same number of samples, but just spread them out. So how would you do that in practice? And what does that correspond to on the magnet? So remember, if you go up to higher spatial frequencies, that just means the gradient was on longer. So it could be either either the gradient was on longer, so that means you extended the readout so that the gradient was on longer, or equivalently, you just doubled the size of the gradient. So you could either just record for twice as long, which would just allow the same gradient to wrap up the spins up to a higher spatial frequency, or you could just turn the gradient, double the size of the gradient, record the same. So that's what's actually, so either the length or the time or some combination is what's causing you to record higher spatial frequencies. So now the question is, what does that do? So you can imagine, if it's big, if it's expanding here, it's probably going to shrink down here, and that's what happens. So what happens is, here's your brain. So when you reconstruct this, what do you get? You basically get a shrunken image. So the image will be, half as big as it was before. So the image will be like this big. So, but that's not all it is. So what happens when you do this is it causes, because you're sampling with a bigger space. So this guy is delta kx. Delta kx has increased, and so by that previous argument, what happens is the replicas are going to come in, and so there'd be a replica on this side right here, like this, that will have intruded, and the other replica will have sort of intruded on this side as well. So now there's a little subtlety here. What do you see on the scanner? Well, it turns out the scanner is always going to give you a square picture. So the scanner will give you this picture. So if you actually just do the inverse Fourier transform, what you'll get is a rectangular image. You'll get a rectangular image, but the scanner won't do that. What the scanner will do is there's a square. You notice on the scanner there's a square there. It will show you a square image, and that square image will look like it's wrapped around. So this thing looks like the cutoff part of the frontal lobe that got sort of wrapped around to here. And then likewise there'll be an occipital lobe here that looks like this piece of the occipital lobe that was off the edge that got wrapped around to here. You could say in real life what's happening is it's just the two replicas of the right replica and the left replica have come in and overlapped. So the scanner will fill that in for you, and what is it doing? It's actually sort of duplicating some of the data. So in other words, this thing here is basically the same thing as this data here. So it will sort of pad the data out to a square. But the bottom line is, you don't like it because something has sort of come in and overlapped your image. So what happens to the voxels in that case? Well, they get thinner. So they're thinner just in one axis. So they're still the same thickness that way, but they're thinner in that axis. So if this is our basic image, with square pics, square pixels. So now we end up with, x pix half width. So we increased our spatial resolution, and that makes sense because we're recording higher spatial frequencies. But the replicas intrude. And that looks like wraparound. But the scanner makes a square picture, so this is the scanner image. So you still end up with a square picture. So you can sort of still see the whole brain, but you can see something is wrapping into it. If they just showed you this picture, it would be like, whoa, it just looked like it was folded, and you couldn't see the whole brain. So that's not good. So what do we do if we want to push the replicas out? We would just do the exact opposite of that. And so the opposite of that would be to basically do, 2 times the samples to same spatial frequency. So in this case, what we do is we now have the same k-space. So that means keep the number of wraps in spin phase the same. So keep the gradient the same, but just record more samples. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 samples, still recording 1, 2, 3, 4, 5 that way. So how do you do that? You could just record the data faster, leave the gradients all the same, and record the data twice as fast. Take twice as many samples over the same amount of time as the gradient stays on. Or alternatively, you could turn, so you could either take twice as many samples or sample at the same rate when the readout gradient is on, but just do a lower gradient amplitude. And this could apply to the phase encode. I mean, you normally think of it as sort of applying to the phase encode direction. So just do half the size of your phase encode in gradients, and sort of record. So it's basically just the amount of height of the gradient versus the amount of time those things trade off, and so just some combination of that. So if we now do the Fourier transform of this, what do we get? So in this case, we get a rectangular image like this. So the brain will be in there, and now the replicas will have been moved away. So they'll be further away. So these guys went out that way. And the pixel size will be exactly the same as our first one. So we still end with square pixels. The square pix, FOV is 2 times. We'll do the calculations in a second. So what is this called on the scanner? This is called phase oversampling. Which is quite confusing. So why do they call it that? Well, they call it that because you're sampling sort of faster. You're sampling sort of more phase encode steps than you would actually need to in order to sort of get a regular image that wasn't wrapped around. But of course, if somebody has a really long brain, then you want to do this. It's not oversampling. It's just like making the field of view big enough so that their extra long brain doesn't wrap around. But that's what it's caused. That's confusing. What it's called on the scanner, which is to sort of like, it's all relative to this default setup. And so it means phase oversampling means like scrunch in more samples in the kx or ky direction relative to this. And so it's in percent of this. So 120% phase oversampling means like do 1/5 extra, shrink down, increase the number of sampling steps by 20%. So so that's kind of confusing. But let's go through the calculation here just to show how it works. So in this case, the number of pixels is still 10, and except now we're going up to kx equals 10 instead of 5, And the sampling interval now was 2 because we're going in jumps of 2 instead of 1. And so the field of view is just 1 over 1 over the sampling interval. So the sampling interval is 2. So field of view is just 1/2, which is 0.5, which is compared to 1, so it got half as big. And the pixel size also got half as big. So now it's 0.05 instead of 0.1. So you can see those equations are just like mind-numbingly simple equations, just reciprocal. And it's kind of the reciprocal thing. You can sort of think of that as like the real case-based thing, like bigger here, smaller here. It's kind of that's the way a reciprocal is. Okay, so what about this guy? So this guy, now we've got number of samples equals 20, and we're still now going back up to spatial frequency 5 instead of 10 over here, and our sampling interval is 0.5. So we're sampling at twice the rate. So then when we calculate the field of view, we get a field of view equals 2, twice as big, and the pixel size didn't change. So that's actually something that you might want to do. Now, what about something else, which is, what if we just change the pixel size? So it turns out that involves a little bit, yet a different condition. So here we start off with our standard one. Here we spaced out the sampling. That caused the replicas to come in. Here we sort of like did the sampling more densely. That pushed them out. But what if we just want to change the pixel size and not mess with the actual field of view, which is something I just want to go to a higher pixel size, but I want to have the same image. So this is the most practical one. So here's our original K-space. How would you do that? You would just basically make a rectangular K-space like that. So this one is 2 times number of samples to 2 times spatial frequency. So we might often want to do this. And so we would still have 1, 2, 3, 4, 5. And now we would just have the same spacing, but just go out further. So now what's happening is it's the same spacing and spatial frequency, but we just have twice as many samples. And so what does that do? So that, when you Fourier transform that guy, you'll get a square image again, which is kind of a little weird. So you'll get a square image. It'll look the same size, but the pixels will be narrower in this axis, like that. So they'll be just as narrow as they were in this case, but now we will have, by keeping the sampling rate, kept the replicas away. So when you look at the simple calculations here, it's basically, so now the number of pixels is 20, and the maximum spatial frequency is 10 instead of 5, and the sampling interval, however, is exactly the same as it was before, which is 1, and so that means the field of view is the same, which is just 1 over 1, and the voxel size, however, has gone down to 0.05. So this is four more different different cases of messing around with our sampling rate. So that's, so here, so x pix half width and field of view same as a ridge. So so this is what's actually going on. It doesn't feel that way in the scanner. At the scanner, you just have an image. You're not thinking about replicas, but sometimes something will wrap around. And so the question is, how do I fix that? So the way you would fix it, typically, if you get like a wraparound, would be to do some phase oversampling, just basically sort of cause these samples to be, the delta kx to be smaller, and that will push the replicas out. Won't change the size of the image. You'll still end up with the same image on the console, but it will actually sort of get the replicas away. When you actually look at the image that you get as the data, it will be bigger because the field of view is bigger, and so you actually will have a rectangular image when you look at your data, but on this console you won't see that. So that's so that's the confusing field of view. So that's really what the field of view is. It's all about like what is the space, actual real space to the next replica. Now, what's the downside of this? Well, the downside of this is you have to pay for this somehow. So if you're going to get more samples, you have to actually sample more data, and that's going to take more time typically. It doesn't have to take more time. You could instead do the data sampling more rapidly, but in that case you would lose some signal to noise, because remember we said that the rate of data sampling is inversely proportional to the signal to noise, and so and if this is a phase encode direction, then it's just going to be more steps. It'll just increase your scan time because you just got to collect more phase encode steps. So that's the field of view. So one way of thinking about this is as an example of aliasing. And so if you know something about sort of sampling data like audio data, you get something called aliasing. And so I'll just draw a simple example of that. So what happens if, and this is a very sort of intuitive example to me. So what happens if you, so aliasing in time domain sampling. So it's basically replicas again, but this is, to me, is very intuitive. So what we're talking about here is aliasing when we're in this frequency domain sampling. But now we're going to talk about aliasing the same thing. Since it's the Fourier transform, you can go back and forth and sort of see the same thing in either domain. So there's aliasing in the time domain. So what does that mean? Well, say we've got a signal like this. So here's a signal, and we're not sampling it fast enough. So let's say our sampling rate is something like here, and then we've got one here, and then the next time we're over here, the next time we're over here, next time we're over here. So all we did was we just discretely sampled the signal at instantaneous points in time. And then what does that look like? Oh, that doesn't look good. That looks like a really low frequency signal. And that's clearly not right. So what do you do in this case of an audio signal? You have to sample at least twice the rate of the highest frequency in the sample. So, because then if you were at twice the rate of this frequency, you would sort of hit the top and bottom and the top and the bottom, and you would be able to get a crude reconstruction of that signal. If you sample it any less than twice the frequency of the signal, of any frequencies in the signal, then you're going to run into trouble. And what will happen is the signal will come out aliased, meaning that you thought that this was the frequency that was in there, but your sampling of it gave you a smaller frequency, a much lower frequency. So so that's not a good thing. So how do you fix it in the case of sampling? So you could either sample faster, but another more common way is just filter out the frequencies that are too high. So you just, using some kind of filter, just remove any frequency that's any higher than half of my sampling rate. And that's always the safe thing to do, because then if I sample, I won't get I won't run into this aliasing problem. Unfortunately, that's not possible with the brain. So with the brain we can't sort of the brain is a certain size, and unfortunately we can't just sort of cut half of it off, just cut the higher frequencies off effectively, something like that. We just have to sort of deal with it other ways by sampling faster. That's what we're talking, all we're talking about here is just make sure that you sample fast enough in the spatial frequency domain in order to not get the replicas in. But how does this thing cause a replica? So that's the last thing. So let's imagine a slightly higher signal, a slightly higher frequency signal. So here's a slightly higher frequency signal. So what if we sample that at the same rate? What will we get? So here's that's kind of ugly here. Let's make sure that I sampled correctly. It's supposed to be a higher frequency, guys. I put this one wrong here. This guy goes, yeah. Nah. See, what did I draw wrong here? So here, we get this. Here we should be just a little above. Yeah, I made this guy a little bit too short. There we go. Make him a little longer. It should be right about there. Okay, so there's our lower frequency, and now let's work it out on my inelegantly drawn side waves down here. So the bottom line is you'll get a higher frequency down here if you draw it well. So this frequency will this frequency will be a higher frequency, the fake frequency. And so what does that look like if you drew it accurately and looked at a whole bunch of different frequencies? So what it would look like is this is frequency, and say this is the amount of each frequency, and say we went off the sampling rate edge, and there was something like that. So here's our field of view effectively. That's our so this is the field of view of frequencies that we're capable of imaging, but we've got some that are off the edge. And so what happens to them? Well, they just get translated back to here, and so they just basically get added onto the spectrum over here like that. And these just add on top of each other. And what is that? That's a replica coming in. So you can think of, there's another copy of the spectrum over here like this. That's another, so you can see here's one copy and here's another copy. And so it's basically the same thing, bizarrely. So sampling, if we don't sample fast enough in the spatial frequency domain, we get this aliasing, also known as replicas, coming in, very similar to the time domain. If we don't sample fast enough in the time domain, we get a copy of the spectrum intruding from the other side. So this will appear, so even though this thing is actually a really high frequency, say this was, the frequency of this was 100, well, then this is going to be like 120. Well, 120 will sort of go back down and appear as 20. And then, 121 will come back down and appear as 21. So you'll have you just have a perfect replica of the spectrum of frequencies. So this is, time going this way and, frequency going that way. So it's the same, it's the same, bizarrely, it's the same concept of these sort of replicas of the spectrum, except in this case, this is the frequency domain. And so instead of getting replicas of the spectrum, we get replicas of the object. So, okay, I think I'll end there, David, and we'll take some questions.